Now we'll move on to graphing motion area. You can find everything I'm going to talk about in the chapter notes. We're going to take a look at the area under a velocity versus time graph. Let's say we have an object moving at a constant velocity. Let's say the object's moving 4 meters per second for say 15 seconds. What does the area under that graph represent? To find the area, we would take the height times the width, and that would be the velocity times the time. If velocity is the displacement over the time, then the velocity times the time is the displacement. And since the initial time is often 0, we often drop that delta sign. So the area under this velocity versus time graph is how far we've gone. So the velocity times time would be 4 meters per second times 15 seconds. We have a displacement of 60 meters. It's always a good idea to do a check and see that the units cancel out to leave you with meters. Now, people sometimes say, what does that mean in terms of area? 60 meters is not an area. The area represents this distance. It's kind of like a pie chart. There's no pies there. It's just the area represents a quantity. So this was an example with constant velocity. What if we have an acceleration? Here we have an object starting from rest and increasing speed up to 6 meters per second in 15 seconds. What's the area under that graph represent? Yeah, it'll still be a distance, how far we've gone. But now we're only talking about the area of a triangle. So the area of height times width has to be modified with a 1/2. And we have to be sure to use the final velocity. So the displacement is going to be 1/2 times 6 meters per second times 15 seconds. And that's 45 meters. Well, what would happen if we started out at 6 meters per second and we stayed at that constant 6 meters per second? We would have had 6 meters per second times 15. Well, that would have been a rectangle, and that would have been 90 meters. But as you can see, because we started at 0 and increased, we've only covered half that distance, and so that's 45. Another way of looking at the problem is to look at the average velocity. That would be 3 meters per second. 0 plus 6 divided by 2. Does that really work? You can tell by looking at the areas. What would be the area of that rectangle? We get 3 meters per second times 15 seconds, 45 meters. That's the same area as the triangle. It works because the area that we're missing with the average velocity is filled in by this area over here. So the formula V average equals V initial plus V final over 2, that works for constant acceleration as well. Now what if we have an acceleration with an initial velocity? Let's say we start at 2 meters per second and increase our speed to 6 meters per second in 15 seconds. We could use area to find out how far we've gone. I think a lot of people would say, let's just make a rectangle and a triangle out of this. We could take our initial velocity and multiply by time. That would give us the distance traveled due to the initial velocity. Now, what about that triangle? That's the distance we've traveled because we've started with an initial velocity and went up to a final velocity. Well, if we think of it as a triangle, it's going to be 1/2 this height times that width. Well, the height is V final minus V initial, and the width is the time. So we have 1/2 V final minus V initial times time. So we have two separate areas, and now we can add them together to see how far we've gone. That's the displacement. We have a displacement due to the increasing speed and a displacement due to the initial velocity. Plugging in all our values, we get 30 meters and 30 meters. Each area was 30 meters to get 60 meters for the displacement. The V final minus V initial looks like something we've seen before. How about an acceleration? I could just bring the t over, and now I have it. I can just substitute a times t. And now I have a new formula for displacement. It's 1/2 at squared plus VIT. Remember that the slope of that line is the acceleration? We know how to find that. The acceleration is 0.26, repeating, meters per second squared. We can now plug that in for the acceleration, 15 seconds squared plus 2 meters per second times 15 seconds. Hey, we still get 60 meters. It works. Hey, let's check it with that V average stuff we just learned about. If you have the initial is 2 and the final is 6, the V average is 4. You can do that in your head. What's the area of that rectangle? Should be the height times the width. Sure is, 60 meters. Again, you can see that the area that got cut off got filled in here. So we used area to derive a new formula. The displacement is equal to 1/2 AT squared plus VIT. And you can break up the displacement into x final minus x initial and bring the x initial to the other side. Either way, it's the same formula. We've also seen on the graphs that the V average times time is also your displacement, and that the V average can be found from V initial plus V final divided by 2, as long as we have constant acceleration. And of course, we remember that acceleration is the change in velocity over the change in time. Well, let's see what we can do by combining these. I'm going to put in V initial plus V final over 2 for the V average. I can rearrange the acceleration and solve for t. I can eliminate the t. I'll bring the 2 and the a over to the left, switching the VF and the VI. I'm sure you recognize this. Now we'll solve for V final. We get the square root of 2a delta x plus VI squared is the V final. This is very useful for when you're not given the time in a problem, but you are given the distance traveled and the acceleration and the initial velocity. So these are the two new big formulas that you're going to have to get used to using all the time. So let's try some examples. A car has an initial velocity of 5 meters per second and accelerates to 20 meters per second in 3 seconds. Find the displacement. Now you really ought to pause the video and try this. Well, we know that the displacement is 1/2 AT squared plus VIT, but we don't know the acceleration, but we have a formula for it. Hey, we get 5 meters per second squared. Now notice when I do this math, I actually show you the formula and the units. That's what I expect you to do. So we have 22.5 meters due to the acceleration and 15 meters of travel due to the initial velocity. That's 37.5 meters. Let's check that with V average times t. V average is just 5 plus 20 divided by 2. We get 12.5 times 3 seconds. Same answer. It's working. Now we have to graph the velocity versus time and the position versus time. So we're going to start at 5 meters per second. We're going to reach 20 meters per second in 3 seconds. Now, how am I going to get a position versus time graph? By looking at this graph. Yeah, it's the area, but we're going to break it up and see what happens. I want to know how far I went in the first second so I can plot a point down here. The easiest way to find that area is to take the average velocity for this segment. Because we're accelerating, we're reaching 10 meters per second at the end of 1 second. So my average velocity would be 7.5. What's 7.5 meters per second times 1 second? 7.5 meters. So in 1 second, I've traveled 7.5 meters. Where am I at 2 seconds? At the beginning of this time interval, I'm at 10 meters per second. At the end of the time interval, I'm at 15. So what's my average velocity? 12.5 times 1 second. I traveled 12.5 meters in that interval. So where do I put the dot down here? I have to take 12.5 meters plus 7.5 meters, and I'm at 20 meters. And for the last time interval, our average velocity is going to be 17.5 meters per second times 1 second, and I get 17.5 meters. So where do I put the dot? I'm all the way up at 37.5 meters. Now we can see the construction of this graph. What should the slope be down here when we start this curve? The slope of this graph is velocity. Hey, it's not 0. We have an initial velocity of 5. We better start with a positive small slope. And as you can see, the slope keeps increasing because the velocity kept increasing. I'm making a special note that the initial slope is not necessarily 0. You have to look at this graph to see what it is. So we can look at the area of a velocity versus time graph and construct a position versus time graph. And we can look at the slope of a position versus time graph and get a velocity versus time graph. How about we take a road trip in our car for another example? Let's say we travel 60 miles an hour for 2 hours. We hit some traffic for a couple of hours. And then for some crazy reason, we spend the next 2 hours slowing down to a stop. Okay, I know it's unrealistic, but who cares? Let's find out how far we've traveled. Can you see how I got 120 miles? We did 60 miles an hour for 2 hours. You see how I got 160 miles? And that last triangle is 40 miles. We started out at 40 miles per hour, ended up at 0. So we're going to have to find the area of a triangle. Well, that's 40 times 2 is 80 divided in half. We have 40. So what's our total displacement? 320 miles. Okay, what's the V average? Total distance over total time. And you should get 40 miles per hour. So what would a position versus time graph look like for this? At 2 hours, we're at 120 miles. We traveled at a constant speed. This says we've made steady forward progress. Now we have to add 160 to get to 280. That was also done at a constant speed, but it was slower, so the slope is a little lower. In the last section, we're only going to travel another 40 miles in 2 hours, but we're slowing down, so the slope has to gradually approach 0. The 0 slope means we have 0 velocity. Now here's a challenge for you. We're going to start off at 5 meters per second. The object's going to reach negative 10 meters per second in 3 seconds, and then remain at negative 10 meters per second for another second. You need to pause this video and try to make a position versus time graph. I'm going to break this up into 3 areas: a triangle, and a rectangle. How far did we travel in that first triangle? I'm going to use my V average times times technique. 2.5 meters per second times 1 second, I get 2.5 meters. Let's find the area for the next triangle, doing the same thing. We have a 0 velocity, a negative 10. I have an average velocity of negative 5 meters per second. Times 2 seconds, I get negative 10 meters. This means I went forward 2.5 meters and backwards 10 meters. Using the same analysis, I can see that I've traveled negative 10 meters again. I went backwards another 10. I'm setting my position versus time graph up, so I have a lot of room going backwards because I'm going backwards much more than I'm going forwards. We can see that at 1 second I've traveled 2.5 meters, so at 1 second I have to put a dot between the 0 and the 5. If I go forward 2.5 meters, and then I go backwards 10 meters, I'm going to be at negative 7.5 meters. So at 3 seconds, I put a dot here. Well, I've gone backwards yet another 10 meters, so I'm going to be down at 4 seconds, negative 17.5. I never gave information about the initial position, so we assume it's 0. And now we have to connect the dots. We know that this velocity is constant, so that must be a straight line. We know we're changing our velocities all throughout here. So we have to start here, get to that point, and get to this point, all on a curve, because the velocities keep changing. At 1 second, we can see we have 0 velocity. So that means the slope at the top must be 0. We can see over here we have a positive velocity, which means we must have a positive slope. So to connect everything, it's going to be a curve. Now, you'll do a better job if you did this on graph paper. Here's what I'm talking about. 2.5 meters for that triangle. Well, that should be negative 2.5 for that triangle. So at 2 seconds, I should be right back to 0 position. I missed by a little bit. Let's find the average velocity. The displacement, those areas. Negative 17 meters over 4 seconds. And we get negative 4.25 meters per second. Where's that on the graph? Right there. This area is negative 17 meters. Let's find the acceleration for that first time interval from 0 to 3 seconds. Change in velocity over change in time. Well, the final velocity is negative 10 meters per second. The initial velocity is a positive 5 meters per second. Well, the negative sign is due to this difference here. Divide by 3, negative 5 meters per second squared. Now that's the same value everywhere along this line. You can see that in 1 second, we lost 5 meters per second. And if we did the math for this little interval, in another 1 second, we lost 5. So the acceleration is negative 5 meters per second squared the whole way. And what about the second acceleration? There is no change in velocity. It's negative 10 and negative 10. So we have 0 meters per second squared. The graph for that would be pretty easy. We'd be at negative 5 meters per second squared for 3 seconds, and then 0 meters per second squared for the final second. While we're at it, why don't we ask what the area of this graph represents? It would be an acceleration times a time. That's the height times width. Well, acceleration times the time is the change in velocity. And we can see that negative 5 times 3 is going to be negative 15 meters per second. Does that agree with this graph? We started with 5, we ended up with negative 10. Yeah, we have a change in velocity of negative 15 meters per second. So again, we can say that the slope of this graph is the acceleration graph, and the area of the acceleration graph gives us a velocity graph. Just one more example. Let's say we have a car traveling at 10 meters per second. It travels 100 meters, and it accelerates at 4 meters per second squared. How do you get the final velocity? Notice that there's no time in this equation. So you can't use this formula. Not to worry, we have this formula. There's no time in it, but we have everything else. We get 30 meters per second. So here's our answer. Can we check that? Let's see if we can use the average. If that's 30 and that's 10, the average is 20. 100 meters, what's the time? 5 seconds. Now I'll use the acceleration formula, and let's see what we get for the final velocity. Plugging everything in, solve for V final. Looks like it checks out. For more practice, you've got to check the chapter notes. Everything is in here. I have all different numbers for you to try. I already have a video on the ramps with the ball rolling back and forth. You should try that. I'm going to post another video on 2 more computer simulations for you to get practice with. And in the Google Drive on the chapter notes, right next to kinematics is more practice worksheets. There's pages and pages of examples with answers.